13 billion miles from where you're sitting right now, a machine roughly the size of a small car is drifting through total darkness in the space between stars. It was built in the 1970s. It runs on less electricity than the light bulb in your kitchen. And it's still talking to us. That machine is Voyager 2. NASA launched it almost 50 years ago with one job: fly past a few planets, take some pictures, and call it a mission. It was built to last 5 years. It didn't stop. It kept going past Jupiter, past Saturn, past Uranus, past Neptune, and then, in 2018, it did something no human-made object had ever done before it except its own twin. It left the solar system entirely, crossing an invisible boundary where the sun's influence finally gives out and the true emptiness between stars begins. And what it found on the other side broke a good chunk of what scientists thought they understood about space. The plasma was too dense. The magnetic field pointed in a direction nobody predicted. The temperature didn't match the models. Our sun's protective bubble, it turned out, was leaking. None of this was supposed to happen. So what exactly is out there in the dark, and why are NASA engineers still fighting right now to keep a dying 50-year-old spacecraft alive long enough to keep measuring it? To answer that, we have to go all the way back to the beginning. Cape Canaveral, Florida, August 20th, 1977. A rocket sits on the pad, ready to carry a small robotic explorer into the sky. That explorer is Voyager 2, and the reason it exists at all comes down to something almost nobody noticed at the time: a quirk of orbital mechanics spotted by an engineer at NASA's Jet Propulsion Laboratory in Southern California. In the late 1970s and early 1980s, the 4 giant outer planets, Jupiter, Saturn, Uranus, and Neptune, were all going to line up on the same side of the sun. That specific alignment only happens once every 176 years. The last time it occurred, the United States didn't exist yet. The next time it happens, nobody watching this today will be alive to see it. But it meant something enormous was suddenly possible. A single spacecraft could visit all 4 planets in one trip, using each planet's gravity as a slingshot to pick up speed for the next leg without burning a drop of extra fuel. NASA called it the Grand Tour, and they had exactly one shot at pulling it off. So they built 2 spacecraft, Voyager 1 and Voyager 2. Each one was about the size of a small car, wrapped in gold and silver insulation blankets, with a wide white dish antenna bolted on top to keep in touch with Earth. Packed inside were cameras, sensors, and instruments built to measure everything from magnetic fields to charged particles to the faint static of radio waves in deep space. Power came from a small nuclear source, a chunk of plutonium slowly converting its own decay heat into electricity, designed to keep working for decades. But there was something else bolted to each spacecraft that had nothing to do with science at all: a golden record. A 12-inch gold-plated copper disc, sealed inside an aluminum cover along with a needle and cartridge for playback. It was the brainchild of astronomer Carl Sagan, one of the most recognizable scientists on the planet at the time. Sagan and his team at Cornell assembled, essentially, a message from Earth. 118 photographs of our world, 90 minutes of music pulled from cultures across the globe, spoken greetings in 55 human languages, the sound of ocean waves, birdsong, a baby crying, a mother's heartbeat, even a recording of human brainwaves. The logic was as simple as it was audacious. These 2 spacecraft were eventually going to leave the solar system and drift through the galaxy for billions of years. If, in some almost unimaginably distant future, another civilization ever found one of them floating through space, they'd find the golden record waiting for them, a message in a bottle tossed into the largest ocean there is. Sagan later said that launching this bottle into the cosmic ocean said something genuinely hopeful about life on our planet. He wasn't wrong. But before Voyager 2 could deliver humanity's greeting card to the stars, it had actual work to do. And that work was about to rewrite a good part of what we thought we knew about the outer solar system. Its first stop was Jupiter, the solar system's largest planet, which it reached on July 9, 1979, screaming past at roughly 35,000 miles an hour. The images it beamed back were staggering. Storms bigger than Earth swirling in the upper atmosphere, bands of colored gas stretched across the planet like brushstrokes. And the Great Red Spot, a storm that has apparently been raging for centuries, large enough to swallow our entire planet whole. But the real surprise wasn't the planet itself. It was one of its moons. Io, a small world scientist expected to be a dead, cratered rock, turned out to be covered in active volcanoes, some spewing material hundreds of miles into space. Nobody had known moons could even do that. Io remains to this day the most volcanically active body anywhere in the solar system, and that single discovery rewrote planetary science textbooks overnight. Voyager 2 also captured detailed images of Europa, another Jovian moon, showing a smooth, icy shell laced with cracks like a fractured eggshell, and scientists started wondering for the first time whether an entire liquid ocean might be hiding underneath. Decades later, Europa remains one of the most promising places in the solar system to search for life beyond Earth, and it was Voyager 2 that first pointed us there. From Jupiter, The spacecraft used a gravity assist to slingshot toward Saturn, arriving on August 26, 1981. What had always looked like a solid, unbroken disk from Earth turned out to be billions of individual chunks of ice and rock, some no bigger than a grain of sand, others the size of houses, all orbiting in tight, precise lanes. Voyager 2 mapped the rings in unprecedented detail, discovering new gaps, new structures, and small moons hiding inside the ring system that nobody had ever seen. Saturn's actual moons delivered their own surprises. Enceladus, a small world sheathed in bright ice, and Titan, a giant moon wrapped in a thick orange haze with a real dense atmosphere thicker than Earth's own. That alone was remarkable. Most moons in the solar system are bare rock with no atmosphere at all. Here's where Voyager 2 became something genuinely unique. Voyager 1 had also visited Jupiter and Saturn, but its trajectory afterward sent it climbing up out of the flat plane of the solar system entirely, ending any chance of visiting another planet. Voyager 2, by contrast, was still lined up for the rest of the Grand Tour. Its next stop was Uranus, and this is where it entered territory no spacecraft, no telescope, and no human eye had ever examined up close. It reached Uranus on January 24, 1986. Uranus is an ice giant, a pale blue-green world tipped almost completely onto its side. For reasons scientists still debate. The leading theory is a colossal ancient impact that knocked the planet over billions of years ago. But the tilt wasn't even the strangest thing Voyager 2 found there. Uranus's magnetic field was wildly off-center, tilted nearly 60 degrees from its spin axis, and not even centered on the planet's core, as if its internal compass had been knocked completely out of alignment. Nobody has ever fully explained why. Voyager 2 also turned up 10 previously unknown moons and 2 new rings, quietly hiding in the dark, waiting to be noticed. Before this flyby, humanity's picture of Uranus was a flat, featureless blue dot. After it, we knew we were looking at one of the strangest planets in the solar system. 3 years later, on August 25, 1989, Voyager 2 made its final planetary stop, Neptune. And this is where things got genuinely wild. Neptune sits so far from the sun that scientists expected a cold, sluggish, largely uneventful atmosphere. Instead, Voyager 2 found chaos, a massive storm called the Great Dark Spot, similar in scale to Jupiter's famous red spot, churning through Neptune's atmosphere, surrounded by winds clocked at over 1,200 miles an hour, the fastest ever recorded on any planet in the solar system. On a world that receives almost no energy from the sun, nobody has fully explained where all that atmospheric energy comes from. Neptune's largest moon, Triton, delivered maybe the single biggest surprise of the whole mission. It orbits Neptune backward, against the planet's own spin, a near certain sign that Triton wasn't born there at all, but was instead captured by Neptune's gravity after wandering in from somewhere else in the outer solar system entirely. Its icy surface, meanwhile, was actively venting nitrogen gas geysers miles into its thin atmosphere, a frozen world that was, somehow, still geologically alive. That night, JPL threw a party. Chuck Berry, whose song Johnny B. Good had been included on the Golden Record over a decade earlier, performed live for the team, with Carl Sagan among those in the crowd, watching images arrive from a world nearly 3 billion miles away. It was one of those rare moments where science, music, and genuine wonder all landed in the same room at once. And with that, Voyager 2's planetary tour was officially complete. But the spacecraft itself was nowhere near finished. Once Neptune was behind it, NASA formally began what they called the Voyager interstellar mission, a goal that was simple to state and almost impossible to really picture. Keep the spacecraft alive as long as physically possible and find out what actually happens when it reaches the true edge of the solar system. To understand what Voyager 2 was heading toward, you need to understand what the solar system actually is, underneath the planets and orbits. The sun is constantly blowing outward, not wind in any everyday sense, but a stream of charged particles, mostly protons and electrons, blasting outward in every direction at roughly 1,000,000 miles an hour. That stream inflates a colossal bubble around our entire solar system called the heliosphere. Picture a snow globe. Everything inside it, the sun, the planets, every asteroid and comet, sits bathed in the sun's energy and shielded by its magnetic field. Everything outside the globe is interstellar space, the true region between stars. The edge of that bubble, where the solar wind finally grows too weak to push back against the material drifting between stars, is called the heliopause. Nobody had ever reached it, measured it, or even known precisely how far away it actually was. For decades after Neptune, Voyager 2 just kept flying outward. Year after year, the sun shrank behind it. Its signal grew fainter with every passing year. A message from Voyager 2 today takes roughly 19 hours to reach Earth, even moving at the speed of light. Imagine sending a text and waiting the better part of a day just to know it arrived. The discoveries, remarkably, haven't stopped. In recent years, scientists studying Voyager data have picked up on a persistent faint hum, a low-frequency vibration from plasma waves rippling through the thin interstellar gas. It's letting researchers map the density of that region in something close to real time, essentially turning an invisible ocean into something they can listen to, the way you'd hold a seashell to your ear, except this ocean is made of charged particles spread across light years. Voyager 1's plasma wave instrument, its two long antennas stretching 30 feet out behind the spacecraft, has been picking up this hum since 2017. Higher pitch means more electrons packed into a given volume of space, and that pitch has been slowly climbing. The region around our solar system is getting denser. No model from decades ago predicted that either. Step back and look at the whole picture together. For 60 years, scientists sketched the heliosphere on chalkboards, built computer models, and felt reasonably confident they understood the edge of our solar system. Then actual measurements arrived, and almost every prediction turned out to be wrong in some way. The magnetic field pointed the wrong direction, the plasma density was too high and kept rising, the temperature ran warmer than expected, the boundary was leaking, the crossing distances matched when they shouldn't have, and the interstellar magnetic field was strong enough to potentially reshape the entire bubble. Any single one of these would be a significant scientific finding on its own. Together, they describe a solar system boundary that's far messier, far more dynamic, and far stranger than anything drawn in a textbook. And underneath all of it is a bigger point worth sitting with. The heliosphere isn't just an abstract diagram, it's the actual shield protecting every living thing on Earth from the harsher radiation of the galaxy. Thanks to Voyager, we now know that SHIELD isn't a clean, simple bubble. It leaks, it gets compressed by external magnetic forces, and it has turbulent transition zones nobody anticipated. Understanding exactly how that SHIELD behaves isn't just intellectual curiosity. If humanity ever sends astronauts beyond the solar system, they'll have to physically cross the heliopause and enter that same high radiation environment. Voyager just finished mapping for the first time, which makes this data something close to an actual roadmap for a journey that hasn't happened yet. And then there's the golden record, still bolted to Voyager 2's side right now, moving through the dark at roughly 34,000 miles an hour. Greetings in 55 languages, the music of Bach alongside Chuck Berry, the sounds of thunder and laughter and whale song, a mother's voice, and the recorded brainwaves of Anne Druyan, the record's creative director, who would go on to marry Carl Sagan. All of it built to survive in the vacuum of space for roughly 1 billion years. Will anyone ever actually find it? Almost certainly not. Even at its current speed, Voyager 2 would need around 40,000 years just to approach the distance of the nearest star system, and that star isn't even in its path. But that arguably was never really the point. The golden record wasn't primarily a message aimed at aliens. It was a message from us to whoever or whatever might eventually be out there. A small group of people in 1977 deciding to say, in effect, we were here, this is who we were, this is what we sounded and looked and dreamed like, and they attached that message to the two objects that are now, quite literally, farther from home than anything humanity has ever built. Sagan once described Earth, seen from deep space, as a pale blue dot, a single point of light adrift in an ocean of darkness, holding within it every war and every love story and every idea humans have ever had. Voyager 2 is now so far away that if it turned its camera back toward home, the dot wouldn't even be visible anymore. In November 2026, just a few months from now, Voyager 1 will reach a distance of 16 billion miles from Earth, a milestone with its own name, one light day, meaning light itself takes a full 24 hours to cross the gap between the spacecraft and home. No human-made object has ever been that far away. Both Voyagers are still talking to us, their signals fainter every year, their power slowly bleeding away. But they're still out there, still measuring, still sending fragments of data back through the dark. And when the last instrument on each one finally goes quiet, the spacecraft themselves won't stop moving. They'll keep drifting outward, past the distant Oort cloud, out into the wider galaxy for millions, then billions of years, long after Earth is gone, long after the sun itself has burned out. Two small machines, golden records still bolted to their sides, silent messengers from a species that once looked up and decided to say something anyway. What Voyager 2 found at the true edge of our solar system rewrote a meaningful piece of modern astrophysics. Plasma too dense, a magnetic field pointing where nothing said it should, a protective bubble that leaks, a boundary more intricate and stranger than any equation had predicted. None of it was supposed to be possible based on everything we thought we understood. But the universe was never obligated to match our models. Sometimes it just takes a tiny, half-century-old spacecraft running on less power than a light bulb to remind us of that. If you're still with me, subscribe. We dig into stories like this every week. And the next time you look up at the night sky, remember that somewhere out in that darkness, Voyager 2 is still out there, still whispering back, still telling us things nobody expected to hear. Then, in late 2018, The instruments started behaving strangely. The rate of solar particles hitting the spacecraft began dropping fast, while the rate of cosmic rays, high-energy particles flung across the galaxy by distant exploding stars, started climbing just as quickly. Two readings moving in opposite directions simultaneously could only mean one thing. Voyager 2 was crossing the heliopause. On November 5th, 2018, it happened. The data left no ambiguity. The plasma, the hot, thin soup of solar particles, nearly vanished within a single day, replaced almost instantly by cold, dense interstellar plasma. One moment, Voyager 2 was inside the sun's bubble. The next, it was floating in the true ocean between stars, becoming only the second human-made object in history to reach interstellar space. Voyager 1 had done it 6 years earlier, in 2012, but with one key difference. Voyager 1's plasma sensor had failed back in 1980, during its own Saturn flyby, so when it crossed into interstellar space, scientists had to reconstruct what happened using indirect clues, essentially describing a painting while blindfolded. Voyager 2's plasma instrument was still fully functional. For the first time in history, scientists could directly measure the actual material filling the space between stars, and almost nothing it showed them matched the predictions. The first surprise came immediately. The interstellar plasma was denser than expected. Scientists had already anticipated it would be denser than the hot, thin plasma inside the heliosphere. That part checked out. But the actual numbers ran higher than any model predicted. And as Voyager 2 kept moving deeper into interstellar space, the density kept climbing rather than leveling off. That wasn't supposed to happen at all. Interstellar space was expected to be roughly uniform, a thin, even sprinkle of particles stretching in every direction. Voyager 1, traveling an entirely different path years earlier, had recorded the same pattern, a roughly 40-fold jump in electron density between 2013 and 2015, but nobody was sure if that was a fluke tied to Voyager 1's specific route. When Voyager 2 confirmed the same rising density along a completely different path, the fluke theory collapsed. Something out there really is compressing the plasma around our solar system, and nobody's entirely sure what. The second surprise ran even deeper. Before either crossing, scientists had a clear prediction for the magnetic field. Inside the heliosphere, the field is generated by the sun and carried outward on the solar wind. Outside it, the field comes from the wider galaxy, shaped by ancient supernovae and the slow churn of interstellar gas. Two completely different sources, which should mean two completely different directions. The same way a compass needle swings when you cross a real border. It didn't happen. When Voyager 1 crossed, in 2012, the magnetic field on the far side pointed in essentially the same direction as the field inside. Scientists chalked it up to a single data point, maybe a coincidence, maybe an odd crossing location. Then Voyager 2 crossed 6 years later in a completely different spot and got the identical result. Two spacecraft, two locations, two different points in the sun's activity cycle, and the same unexplained answer. As one scientist involved in the research put it, nature simply hadn't read the same papers the scientists had, and had no idea it was supposed to change direction at the boundary. To this day, nobody has a solid explanation for why. As if that weren't strange enough, the interstellar magnetic field also turned out to be far too strong. Voyager 1 measured it at roughly 5 microgauss, already about double the predicted strength. Voyager 2 measured it even higher, around 7 microgauss. That's 2 to 3 times stronger than any model had calculated. And because magnetic pressure scales with a square field strength, a field twice as strong pushes back 4 times as hard. That single fact upended 60 years of textbook diagrams showing the heliosphere as a comet shape, a rounded nose facing forward, with a long tail trailing behind. If the surrounding interstellar magnetic field really is this powerful, it could be squeezing the heliosphere in from every direction at once, pressing it into something closer to a sphere than a comet. Some researchers now think the classic comet-tail heliosphere we've all seen in diagrams for decades may simply be wrong. Then there was the temperature. Interstellar plasma was expected to be, and was, colder than the plasma inside the heliosphere. But it was also noticeably warmer than any model had predicted, not by a small margin. The leading theory is that the heliosphere itself is compressing the surrounding gas as it plows through it, similar to the pressure wave a boat pushes ahead of its hull moving through water, and that compression generates heat. The exact mechanism is still being worked out. Maybe the most unsettling discovery of all, the heliosphere is leaking. Think of it as a shield separating our solar system from the harsher radiation of interstellar space, and it's an effective one. Voyager 1 had already confirmed the heliosphere blocks more than 70% of the galaxy's most energetic cosmic rays, radiation that would otherwise batter Earth, damage DNA, and slowly strip away atmospheres over geological time. It's genuinely one of the reasons complex life on Earth has been possible at all. But when Voyager 2 crossed the boundary, one of its instruments picked up something nobody expected. a steady trickle of particles from inside the heliosphere leaking outward into interstellar space, as if the hull of the bubble had small holes worn into it. Voyager 1 had exited near the nose of the heliosphere, the leading edge pushing through space. Voyager 2 exited near the side, or flank. And that flank appears to be noticeably more porous, letting solar particles seep out the way water works through cracks in a dam. On the interstellar side, Voyager 2 also detected something Voyager 1 never saw. A thin transitional layer just past the heliopause, where low-energy particles stream outward along magnetic field lines and cosmic ray levels sit at only around 90% of their expected outer value. A kind of no man's land between true interstellar space and our solar system's immediate surroundings. Researchers describe it as a disturbed, unsettled region. Even after traveling more than 13 billion miles, neither spacecraft has actually reached calm, undisturbed interstellar space. They're still, in effect, in the turbulent suburbs just outside town. One more detail kept nagging at scientists: the distance itself. Voyager 1 crossed the heliopause in 2012 at 121. 6 astronomical units from the Sun. 1 astronomical unit is the Earth-Sun distance, roughly 93 million miles. Voyager 2 crossed in 2018 at 119 astronomical units, a difference of less than 3%, despite the two crossings happening at different locations, years apart, during different phases of the Sun's 11-year activity cycle. The heliosphere was expected to expand and contract with that cycle, breathing in and out like a lung, which should have produced noticeably different crossing distances. It didn't. That result suggests the heliosphere is far more rigid and stable than anyone had modeled, possibly held in check by that unexpectedly powerful interstellar magnetic field, acting almost like a straitjacket, limiting how much the bubble can actually expand or contract. All of these discoveries mean nothing, of course, if Voyager 2 simply runs out of power, and that threat is very real. Each spacecraft is powered by radioisotope thermoelectric generators that convert the heat of decaying plutonium into electricity, a source that fades a little every year. Voyager 2 loses about 4 watts annually. That doesn't sound dramatic, but the spacecraft is already operating on an almost non-existent margin, currently running just 3 active science instruments in an environment where temperatures hover near minus 450 degrees Fahrenheit. Since 2024, that shrinking power budget has forced NASA to start permanently shutting down instruments on both Voyagers, and every shutdown is irreversible. There's no repair mission possible for something 13 billion miles away. Which is why, in the summer of 2026, JPL engineers attempted something they nicknamed the Big Bang. The idea was simple to describe and genuinely terrifying to execute. Switch off certain power-hungry components and swap in lower power replacements, all in a single simultaneous action. The complication is that many of those components don't just draw power, they also generate waste heat that keeps other parts of the spacecraft from freezing solid. Swap things one at a time, and something critical could cool past the point of no return before its replacement takes over. So it had to happen all at once, with no margin for a second attempt. Every command takes about 19 hours to reach the spacecraft, and another 19 for a response to come back, meaning almost 2 full days of waiting after pressing the button, with no way to know in advance whether you just killed a 50-year-old spacecraft. The team spent months simulating and debating the plan through late 2025 and early 2026, partly because the one dish on Earth large enough to communicate with Voyager 2 was offline for scheduled upgrades during that window anyway. In May and June of 2026, they ran a power test and a thermal test on the real hardware. Both passed. In July, they sent the actual command. It worked, freeing up nearly 10 watts of power, enough to keep all 3 of Voyager 2's remaining instruments running for at least another year. Without it, NASA would have had to shut down a 3rd instrument before the end of 2026, leaving only 2 functioning sensors in the one place in interstellar space where humanity currently has any presence at all. Mission manager Kareem Badarudin has described it as the product of an entire year's work, with nearly every team member contributing. NASA is now planning to attempt the same maneuver on Voyager 1, which is even farther away, in the months ahead. It's worth asking why NASA is investing this much effort into a spacecraft built during the Ford administration. The answer is straightforward. There's simply nothing to replace it with. No other mission is anywhere close to interstellar space, and none is funded to get there anytime soon. The closest relevant project, the Interstellar Mapping and Acceleration Probe, launched in 2025, studies the heliosphere's boundary remotely from inside the solar system. It isn't going out there itself. That leaves Voyager 1 and Voyager 2 as humanity's only direct sensors in interstellar space. When they finally go silent, that window closes, and nothing is scheduled to reopen it for decades, possibly longer.